The following is a sample of e-learning courseware developed by Jet Maintenance Consulting Corporation. Welcome to the Fans and NextGen overview. In the next few minutes, we will discuss upcoming mandates in the United States and Europe that require airline operators to upgrade and install certain avionics systems. These upgrades will meet the requirements of the Future Air Navigation System, or FANS, and the Next Generation Air Traffic System known as NextGen. In this courseware sample, we will look at the history of older avionics systems, explore why these upgrades are needed, and discuss how they benefit the aviation industry. In order to proceed with this course, there are a few acronyms and definitions that you need to understand. The first of these is FANS. FANS is an acronym for Future Air Navigation System. FANS consist of avionics systems which provide direct data link communication between the flight crew and air traffic control, as well as the flight crew and the airline operations center. The communications include air traffic control clearances, pilot requests, and position reporting. It can also include event reports, such as leaving the gate or touching down at a destination, reporting of maintenance issues, and engine condition reporting. ADSC. Automatic Dependent Surveillance Contract, or ADSC, is the ability to transmit the position of the aircraft from the flight management system via VHF radio or satellite communication on a predetermined schedule to an air traffic control listening station. Datalink. A datalink is the means of connecting one location to another for the purpose of transmitting and receiving digital information. For our purposes, datalink is data transferred between the aircraft and air traffic control, or the aircraft and the airline operations center. NextGen. NextGen is an acronym for the Next Generation Air Transportation System. It is the new air traffic control system due for implementation across the United States in stages between now and the year 2020. GPS technology will be used to shorten routes, save time and fuel, reduce traffic delays, increase capacity, and permit air traffic controllers to monitor and manage aircraft with much greater safety margins. ADSB Out. Automatic Dependent Surveillance Broadcast, or ADSB Out, is a function of the aircraft's onboard avionics that periodically broadcasts the aircraft's three-dimensional position, velocity, identity, and flight path to air traffic control ground stations and other aircraft equipped to receive it. ADSB Out is part of the FAA Next Generation Air Traffic Control System mandates. Performance-Based Navigation, or PBN. Performance-based navigation utilizes the accuracy of GPS technology. It is a framework for defining a navigation performance specification along a route, during a procedure such as an approach or a departure, or in a block of airspace. In order to use these routes, procedures, and airspace blocks, an aircraft must comply with the specified operational performance requirements. Required Navigation Performance, or R&P. Required navigation performance refers to the level of navigation performance required for a specific route, procedure, or a specific block of airspace. As an example, to fly a route specified as RNP2, the aircraft must be able to calculate its actual position to within 2 nautical miles of where it actually is. To fly an approach specified as RNP.3, the aircraft must be able to calculate its actual position to within 0.3 nautical miles of where it actually is. Now that we have covered some acronyms, we will look at an overview of both the Future Air Navigation System and the Next Generation Air Transportation System. The goals of FANS and NextGen are to allow more aircraft to safely and efficiently utilize a given volume of airspace and to improve safety and performance related to communication, navigation, and surveillance in air traffic management activities in the United States and around the world. The first thing we will discuss is the history of avionics systems and air traffic control procedures that led up to the development of the Future Air Navigation System. Air traffic control radar only has a range of about 200 nautical miles. Therefore, once an aircraft is beyond 200 nautical miles from land on an oceanic route, conventional radar position reporting is lost. This makes it difficult for air traffic controllers to maintain an accurate picture of air traffic over the ocean. Because this radar contact is lost, flight crews are required to report their position and altitude to air traffic control using high-frequency radio at predetermined intervals during oceanic flights once they were more than 200 miles from land. This can cause problems because HF radio is unreliable, affected by weather and solar flares, and thus subject to frequent outages. Another difficulty presents itself when a flight plan requires changes because of storms or air traffic concerns. All flight plans must be verified between air traffic control and the flight crew. Prior to FANS, the air traffic controller reads the flight plan to the flight crew, and the crew reads it back to the controller over VHF radio. This typically takes a long time to accomplish, especially for longer flights. Miscommunication often happens during the voice exchange, causing the process to have to be attempted several times before it is completed. This can lead to controller and flight crew stress and also plays a role in arrival and departure delays. The Future Air Navigation System provides a means for direct communication between the pilot and air traffic control through Datalink technology. Very high-frequency radio or satellite communication systems are used to enable digital transmission of short, relatively simple text messages between the aircraft and air traffic control. FANS also provides a means for automatic position reporting in areas where conventional radar capabilities are limited, such as an oceanic route. The components of the Future Air Navigation System include Air Traffic Control Data Link, Required Time of Arrival, or RTA, and Airline Operational Control, or AOC. Let's define what each of these components actually means. Air Traffic Control Data Link replaces some of the voice communication between the flight crew and air traffic control with text messaging and automatic position reporting. ATC Data Link is made up of Automatic Dependent Surveillance Contract, or ADSC, and Controller Pilot Data Link Communication, or CPDLC. ADSC is the ability to automatically transmit the position of the aircraft from the flight management system via VHF radio or satellite communication to an air traffic control listening station. This provides air traffic control a more accurate picture of air traffic in a particular block of airspace than the previous method of voice reporting. Flight crews on oceanic routes are relieved of voice position reporting requirements because the aircraft automatically reports its position through the data link at predetermined intervals. Controller Pilot Data Link Communication, or CPDLC, is the data link application that enables two-way text messaging communication between the cockpit and air traffic control, or the flight crew and the airline operations center. It contains a set of predefined messages for clearances, requests, and routine message traffic. Free text or non-predefined messages can also be transmitted over the data link network. The Flight Management Multifunction Control Display Unit shown here illustrates an air traffic control approved pre-departure clearance sent to the flight management system via CPDLC. The flight management system will update the current flight plan based on revised clearances received by air traffic control via CPDLC. Air traffic control can directly initiate changes to a flight plan via text message, and flight crews may request deviations to or replacements of the filed flight plan. The flight crew acknowledges the clearance, and the active flight plan is automatically updated. As you can imagine, this process is much faster than using voice communications. In this example, the flight crew is making a request to air traffic control to climb to 35,000 feet due to aircraft performance. They have typed their request into the Flight Management System MCDU and will press the line select key next to Send to make the request. Air Traffic Control responds that the request is approved. The crew acknowledges the approved request by pressing the line select key next to Wilco, and then they climb to 35,000 feet. The required time of arrival component of FANS gives flight crews and/or air traffic control the ability to assign a time constraint to a waypoint or destination, allowing the aircraft to reach a specific point at a specific time. The aircraft cruise speed is automatically adjusted by the flight management system to achieve the RTA. This is useful for airport arrival scheduling and will help to reduce controller workload, arrival delays, aircraft flight times, and fuel burn. This example shows the flight management system required time of arrival page for the waypoint LOACH. Note, the aircraft will fly at Mach 0.825 to reach the waypoint at 1955 Zulu time and will be at 33,000 feet when it gets there. The Airline Operational Control, or AOC Datalink, provides provisions for data communications between the airline and the flight crew through the flight management system. It allows the airline and the aircraft to exchange information concerning things such as new routes, position reports, updated weather information, as well as many other types of operator-customized information through the Datalink network. The graphic shows examples of types of information that can be exchanged. This video gives a good explanation of some of the advantages of Datalink communications.
In India, and contact gate
106. Listen, you can hear a quiet communications makeover as NextGen moves aviation from voice to text. Data communications is more efficient, flexible, and safe. And combined with other NextGen technologies, Datacom opens up great possibilities for the future. This becomes more important as traffic increases and we accommodate new users of the national airspace. Old two-way voice radio won't be able to keep up. Here's how Datacom speeds up the departure clearance process. Each flight crew receives route instructions from an air traffic controller prior to taxiing. The pilot of the voice-only communication plane in red listens to the transmission from the controller,
29 Papa X-ray Victor,
then repeats it to make sure he has transcribed everything correctly.
Okay, so that'll be the new one, radar vectors, dual, J6, Danner, Ravine, J64.
Sometimes this takes more than one exchange before everything is clear, and the process takes several minutes depending on how complex the route information is.
After Newell, it's J60.
J60 after Newell.
If there are reroutes to deliver, the process bogs down even more. With the Datacom-enabled plane in blue, the controller sends digital route information directly to the plane's Datacom receiver. The pilot simply reads the text display and presses Wilco for Will Comply. Then the instructions are loaded directly into the onboard computer system. This takes only seconds. When we look at this process across the operation, the time savings are significant. Those time savings mean a more efficient system. In this scenario, while just 2 voice-only planes have been cleared for takeoff, 5 Datacom planes are already on their way. As more Datacom planes are cleared for takeoff in mere seconds versus minutes, the time savings and departure volume continues to increase. This is the key benefit of Datacom in the departure clearance process. By increasing efficiency of operations nationwide, the result is fewer delays from the outset. With Datacom, controllers will be able to transmit complex reroute information to several planes at once in a sector. The time savings will be significant. Controllers can adjust routes earlier and more gradually, and see the impact of these changes on all planes in the area. The cost savings in terms of limiting delays, reducing fuel use, and streamlining traffic flow will be huge. NextGen is transforming flight routing procedures, increasing efficiency, flexibility, and safety. These changes to our airspace translate into time and money saved for airlines and a better experience for the traveling public.
Now let's take a look at the next generation traffic system being developed in the United States and other areas of the world. Note, for purposes of this course, our focus will be on GPS navigation and ADS-B out. ADS-B in may be a topic of training at a later date. Today, air traffic control relies on conventional ground-based radar surveillance that consists of primary surveillance, which identifies the aircraft position in relation to the radar station, and secondary surveillance, which interrogates the aircraft transponder for information such as identification and altitude. Using this information, the aircraft position identifier, altitude, ground speed, range, and bearing are displayed on an air traffic controller screen. Because older ground-based surveillance only reports information once per radar sweep, about every 4 seconds, it is not by design accurate enough to support the growing number of aircraft in today's airspace. Large vertical and lateral separation between aircraft in cruise flight is required to safeguard against potential collisions. Approaches and departures are also designed to keep aircraft safely separated. NextGen will transform the world's air traffic control system from an aging ground-based radar system to a satellite-based system using ADS-B out. GPS technology and ADS-B out will be used to shorten routes, save time and fuel, reduce traffic delays, and increase available airspace. Let's take a look at the components that make up a NextGen avionics system. First, the aircraft is equipped with a GPS receiver and ADS-B out technology. Because the aircraft is GPS equipped, it can meet performance-based navigation criteria and fly routes and approaches that require a certain navigation performance or R&P. The aircraft GPS receivers supply extremely accurate four-dimensional position information to the flight management system. Using ADS-B out, aircraft automatically broadcast this position information to ATC ground stations at fixed 1-second intervals using the aircraft transponders. Broadcast information includes the aircraft position, altitude, velocity, identity, and flight path. This provides a very accurate and current picture of all aircraft in a particular airspace block to air traffic control. It allows reduced separation between aircraft and it increases safety. GPS technology also upgrades the aircraft's navigation performance, allowing it to take advantage of performance-based navigation. R&P allows for reduced separation between aircraft, more direct routes saving time and money, and shorter flight times for aircraft that are equipped to meet the requirements. Aircraft able to meet R&P requirements are given preferential routes and clearances over those who cannot meet R&P. This is known as the best equipped, best served concept. R&P is now required in certain oceanic regions throughout the globe. R&P 4 and R&P 10 are typical requirements for oceanic tracks. R&P 1 down to R&P 0.3 is typically required for R&P approaches. Examples of airports with R&P approaches include Atlanta, New York's JFK and LaGuardia, Seattle, and many, many more. Many international airports also utilize R&P approaches. This video illustrates the advantage of using R&P over a conventional approach at George Bush International Airport in Houston. Note, there is no audio in this video. Thank you for watching. We at Jet Maintenance Consulting Corp. hope you enjoyed this sample of our courseware. Please visit our website at www.jmcnow.com to explore our aircraft maintenance training, engineering, and technical publications capabilities and check out our training portal at jmcc.inquisicr4.com.